Think about it. Every single time you click a movie on a streaming service, make a credit card purchase, or even just scroll through a social media feed, you're leaving behind a digital footprint. And that footprint is meticulously recorded and stored in traditional, everyday databases by businesses all over the globe. But here's the thing. There is a massive, invisible chasm between how a business records those everyday transactions and how modern artificial intelligence actually consumes information. Today, we're exploring a fascinating and literally game-changing topic: the critical link between standard operational data and the advanced analytical models powering machine learning. If you've ever wondered how a basic collection of sales receipts or user profiles gets fed into the deeply complex mathematical models that predict our behavior, you are in the exact right place. In this explainer, we're going to dive deep into the specific analytical models that make this translation possible. We'll be focusing heavily on data frames, matrices, and arrays. And then we'll pull back to give you a comprehensive chapter summary of the entire modern data model landscape, showing how different database architectures support everything from everyday operations to the absolute cutting edge of AI.
So right off the bat, the fundamental problem we face at the start of any machine learning project is a matter of strict translation. Traditional machine learning algorithms just cannot read standard relational databases. A standard operational database organizes its data into familiar rows and columns, right? It's like a neatly organized filing cabinet full of distinct customer profiles, individual inventory items, or timestamp sales receipts. It's human readable, and it's totally logical for business operations. But machine learning algorithms and neural networks, they don't think in terms of user profiles or receipts. They require massive, multi-dimensional grids of pure numbers to function. They rely entirely on complex linear algebra operations to spot hidden patterns and make their predictions. I mean, a mathematical equation can't multiply a user profile by a sales receipt. It can only multiply a number by another number. So the big question becomes, how do we cross this chasm? How do we take that highly structured, relational business data and warp it into the pure numerical format that an algorithm absolutely demands?
To answer that, here is our roadmap for today. 1. The bridge to AI. 2. Data frames and matrices. 3. Encoding for algorithms. 4. The data model landscape. And finally, 5. Implicit versus explicit schemas. Let's get right into it.
Okay, Section 1. The bridge to AI, connecting relational data to algorithms. To actually extract information from standard databases and shape it up for predictive models, data scientists rely on a completely different set of tools than your typical software engineer. The secret weapon here, the ultimate bridge between these two worlds, is the data frame. Found in analytical languages like R or in Python's incredibly popular Pandas library, and even in massive distributed systems like Apache Spark, data frames act as the translation layer. Now, conceptually, a data frame might seem pretty similar to a relational database table because it supports bulk operations. You can filter rows, group information, aggregate totals, and join disparate datasets together. However, there's a fundamental operational difference. SQL databases are highly declarative. You simply tell the database what final result you want, and the internal engine figures out how to go fetch it. Data frames, on the other hand, allow data scientists to programmatically and incrementally wrangle data. A data scientist will write code, often running locally on their own machine, to load raw data, strip out missing values, standardize formatting, and apply really complex transformations step by step. They're meticulously crafting the exact mathematical state needed before the data ever touches a neural network.
And this required transformation often means fundamentally reshaping the geometry of the information itself. Imagine a user, let's just call him User 100, who decides to watch and rate a newly released science fiction movie. In a standard operational system, that action is recorded as a single, neat row in a relational database. User ID 100, movie ID 50, a rating of 4 stars, and today's date. It's just a discrete recorded event. But an algorithm building a recommendation engine cannot interpret a list of discrete events. It needs a grid. So the data scientist programmatically pivots that information. The movie, which was once just a single data point inside a row, is transposed to become an entire column of its own. The user becomes a single continuous row. Suddenly, User 100's specific 4-star rating is no longer just a receipt. It is a highly specific coordinate point intersecting a vast mathematical grid. By pivoting the data like this, every single user and every single movie form an enormous, interconnected web of numerical coordinates.
But when we pivot data into these massive grids, we run into a really fascinating architectural hurdle. Think about it. A single person might watch and rate maybe a few hundred movies in their lifetime. But a streaming platform's catalog contains tens of thousands of titles. So when we create a row for a user and columns for literally every movie in existence, the overwhelming majority of those intersections will be completely blank. In the data science world, this architecture is called a sparse matrix. Now, if an engineer attempted to create a traditional relational database table with 50,000 columns where 99% of the cells were completely empty or null, well, the relational engine would choke. It would bloat with unnecessary storage overhead and likely crash during a simple query. But analytical models rely heavily on arrays, implemented through specialized mathematical libraries like Python's NumPy. And these arrays allocate memory completely differently than a relational database. They are specifically optimized to ignore all that empty space efficiently and perform lightning-fast linear algebra operations exclusively on the populated numbers. This gives algorithms the computationally superior structure they absolutely demand.
Moving right along to Section 2, Encoding for Algorithms, Turning Categories into Numbers. So we've established that algorithms thrive on arrays and matrices, right? But there's a major catch to this architecture. Mathematical matrices can only hold numbers. This is a severe bottleneck when our operational databases are packed with rich, non-numerical context. Think about the descriptive elements of a business, the text descriptions of products, the specific genres of a film, or even exact publication dates. How on earth do we feed these rich concepts into an algorithm that strictly speaks the language of math? Well, data scientists have to apply some pretty clever translation techniques to mathematically quantify everything. Take a date, for example. An algorithm cannot interpret a text string like October 28th. It has literally no concept of a calendar. Instead, a date has to be translated into a calculation of distance. It might be scaled into a floating point number representing the exact number of seconds that have elapsed since a specific epoch in time. This allows the algorithm to mathematically measure the distance or closeness between two events, basically turning time itself into pure geometry. While turning dates into elapsed time is relatively straightforward, text-based categories require a far more destructive mathematical trick. Categorical data refers to things that fall into distinct, finite buckets, like a customer's subscription tier, the color of a car, or the specific genre of a movie. Comedy, drama, and horror are human words containing human context. But comedy means absolutely nothing to a linear algebra equation. As we said earlier, you cannot multiply drama by the number 5. Therefore, data scientists must obliterate the text entirely in order to preserve its meaning within a mathematical universe. The absolutely crucial point here is that we utilize a specific technique called one-hot encoding to handle these finite categories. One-hot encoding is the bridge that definitively strips away the human language while perfectly retaining the distinct categorization that the machine learning model needs to understand the relationships between different items. The process of one-hot encoding is mechanical, but honestly, it's brilliant. Let's walk through how a data scientist would categorize a single horror movie for a neural network. Step 1. The data scientist completely deletes the column that contains the text words, just gone. In its place, they create a brand new distinct column for every single possible category value that exists in the database. So now there is a dedicated comedy column, a dedicated drama column, and a dedicated horror column. Step 2. For our specific movie row, the algorithm places the number 1 in the horror column, indicating a positive match. Step 3. It places a 0 in all the other newly created genre columns. The text is gone. By turning every single human concept into its own binary column of simple ones and zeros, we give the linear algebra algorithms the absolute bedrock of pure numerical input they require. This simple trick is exactly how artificial intelligence functionally comprehends human categories.
All right, let's step back a bit for Section 3, the data model landscape, zooming out.
We've just taken a massive deep dive into the highly specialized ways data is wrangled, pivoted into arrays, and numerically encoded specifically for machine learning. But the data frame and the array, they're really just pieces of a much larger architectural puzzle. Let's zoom out and summarize the entire modern landscape of data models used by organizations today. Despite being invented over half a century ago, the relational model remains absolutely ubiquitous. It forms the backbone of traditional business analytics and massive data warehousing operations, often utilizing highly structured star or snowflake schemas. On the complete opposite end of the spectrum, we have the document model, which is highly specialized for storing isolated, self-contained chunks of data, typically in JSON format, where elements rarely interact. Then there are graph models, uniquely engineered to prioritize the intricate relationships and connections between individual data points. We have the analytical models like DataFrames and Arrays for statistical analysis that we just spent time exploring. And finally, event sourcing models, which capture highly complex business domains by recording a never-ending, unchangeable log of actions. Every single layer of modern software relies on choosing the right underlying data model to hide its operational complexity. When deciding between these tools, architects have to deeply understand the nature of their domain, because the conceptual differences are staggering. Just look at the contrast between document and graph architectures. A business would choose a document model when their data objects are almost entirely isolated, like saving a user's standalone application settings or an independent blog post. The data is totally self-contained. But this model entirely fails if you're building something like a social network recommendation engine. For that, you absolutely need a graph model. Graph models are built for environments where anything is potentially related to everything else. They are designed specifically to execute multi-hop traversals, allowing an application to effortlessly ask questions like, which movies were liked by the friends of this specific user? A document database would struggle immensely to map that web, while a graph database, utilizing specialized query languages, traverses those complex multi-hop connections with lightning speed.
Another highly specialized and, frankly, fascinating architecture in our summary is event sourcing. Most traditional databases just store the current, up-to-date state of a system. If you change your address, the database overwrites the old one. Simple, right? Well, event sourcing behaves entirely differently. It uniquely models data as a continuous append-only log of immutable events. Think of it like an old-fashioned accountant's ledger, written entirely in permanent ink. If a mistake is made, you cannot take an eraser to the ledger, you must append a brand new correcting entry. It records everything that has ever happened as an unchangeable historical fact. This provides an incredible perfect audit trail for complex business domains like banking or e-commerce. However, querying an infinite log just to find out a user's current account balance is computationally exhausting and slow. So the data in an event sourcing log is continuously translated and aggregated into what are called materialized views. This gives the business fast, read-optimized snapshots of the current state, all while preserving that pristine underlying history.
Which brings us to Section 4, Implicit versus Explicit Schemas Enforcing the Rules.
Across this incredibly diverse landscape, from rigid relational tables to sparse mathematical matrices, interconnected graphs, and immutable event logs, we have to understand how these systems actually govern the information they hold. And this introduces the critical concept of schemas, and specifically, the massive difference between how relational and non-relational databases enforce their structural rules. It ultimately comes down to when the data gets inspected. Relational models strictly enforce an explicit schema, commonly known as schema on write. The database acts like a bouncer at a club. It checks the data the exact moment the application attempts to save it. If a piece of data doesn't perfectly fit the predefined columns and data types, it is outright rejected. No exceptions. Conversely, non-relational models like document databases typically utilize an implicit schema, or schema on read. The database itself is entirely agnostic. It stores whatever raw information you hand it without checking a single thing. Now, this incredibly fast write capability comes with a major trade-off. It places the entire burden of understanding and validating the structure directly onto the application code that has to retrieve the data later.
This inherent trade-off leads to a universal truth in data engineering, wonderfully encapsulated in this concept. Your application most likely still assumes that data has a certain structure, it's just a question of whether the schema is explicit or implicit. As this highlights, structure is never truly destroyed or absent, it is merely relocated. Even if you're utilizing a highly flexible so-called schemaless document database, the software engineer writing the application code still absolutely expects to find certain fields formatted in certain ways. I mean, if the code expects a numerical integer to calculate a total, but the database hands back a text string because there were no rules enforced on write, the application is going to crash. The structural responsibility simply shifts from the strict database engine to the complex application codebase. Whenever an architect chooses a tool from the data model landscape, they are always balancing the ease and flexibility of writing data quickly against the rigid complexity of safely reading it later.
Wow, we have covered a lot of ground today. Our journey has mapped out exactly how the raw data generated by our daily operations is transformed. We started by exploring the deep chasm between relational databases and the mathematical necessities of machine learning. We detailed how data scientists leverage DataFrames as a programmatic bridge, carefully wrangling data locally before pivoting it into the vastly superior, sparse arrays required for linear algebra. We witnessed the destructive but totally necessary translations of dates and text, utilizing techniques like one-hot encoding to turn human concepts into the strict binary language of artificial intelligence. Finally, we pulled back to summarize the diverse landscape of foundational data models, from document and graph to event sourcing architectures, and the inherent trade-offs between explicit and implicit schemas that govern them all. We have seen how relational tables literally have to be warped, stretched, and mathematically quantified just to feed today's modern algorithms. Which leaves us with an exciting and honestly provocative thought. As our analytical and AI ambitions continue to aggressively grow, and as we rely more heavily on increasingly complex neural networks, how will the very shape and structure of our foundational data models inevitably evolve in the years to come? Will a completely new, native architecture emerge?
Thank you for exploring this explainer with me, and keep questioning the data.